Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we'll discuss one new topic, which is module 3, where we will discuss the fiber length. So analytical approaches of measurement and analysis. So we will not discuss in detail the measurement techniques, but after getting the test data, how to analyze and the basic understanding of the principles, this we will discuss here. Before we go to the analytical part, first let us understand the basic terms. Okay, so fiber length is supposed to be one of the most important part in textile material. Okay, so if you see, they are used in quality assessment, fiber breakage study, machine safety, and combing efficiency, and there are many other applications. So measurement of fiber length is very important. Like if we want to know the length of cotton, so we have to test using different techniques that we will discuss, and length of cotton is extremely important as far as quality of yarn and fabric is concerned. So if you have higher length, two cotton fibers, one is mean length is longer fiber, another is short fibers. So longer fiber will result higher strength of yarn due to higher frictional contact, higher contact area will be there, and which will result better yarn strength. And also, suppose two fibers, fiber A is a long fiber, fiber B is short fiber, and we are trying to produce yarn of same count. And if we apply the same level of twist in both the cases, the yarn made from fiber A will result higher strength, and whereas yarn made from fiber B will result lower strength, and level of twist is kept initially same. Now, if you want to keep the strength same strength, we have to impart lower twist in yarn A, and lower twist will result, suppose now yarn A we are producing with a lower twist, lower twist will result softer yarn structure, and the light reflection will be uniform, which will result the improvement in luster. So we see that yarn fiber length measurement is extremely important, which will effectively control the characteristics of yarn. Now coming to the fiber breakage study. In different spinning process like blow room, carding particularly, in this processes fiber breakages takes place. So to know the level of breakages, fiber breakages, we should test the fiber length before and after blow room. Similarly for carding. So if there is any breakage which is undesirable, like level of breakage is high, so that we can change the setting of the blow room or carding. And machine setting also depends on the fiber length. For short fibers, the roller to roller setting will be, distance will be lower, just to reduce the floating fiber. And also to assess the combing efficiency. Combing's function is to remove the short fiber. This is the prime function. So how much fibers are being removed from the combing lab, feed lab, that can be assessed by testing the fiber length before and after combing. So next characteristics is that the length and fineness are sometimes related in natural fiber, whereas for man-made fibers length and fineness can be controlled separately. So that's also one important parameter. For cotton, if we have longer fiber, as it grows naturally, the longer fiber will have generally little bit higher diameter, thickness will be more. Whereas in case of man-made fiber, length is basically fiber is initially we get in the continuous form, then we cut the fiber to make it a staple fiber, and that can be controlled. Cut length of man-made fiber is often influenced by fiber length of natural fiber. So when we are talking about to blend the man-made fiber like polyester, if we want to blend with the cotton, in that case, and cotton fiber say mean length is around say 25 or 30 25 mm or say 30 mm. So polyester fiber length we cannot keep longer length. So we have to select a cut length of a lower cut length. So there are various parameters through which fiber length can be expressed. These parameters are staple length of fiber. So I will show you the fiber sample, how to measure the staple length. It's basically measured by hand. So let me show how to get the staple length. So we can take the small tuft of fibers and then by hand, if we draw and double repeatedly, in this fashion, and we will keep this fiber tuft on the finger, and from there we can assess the rough estimation of the fiber length. That I will discuss in detail. Mean length. This mean length depends on the definition of mean length, depends on the type of test. Like in comb sorter, the definition of mean length is different from so in comb sorter diagram we calculate the mean length of fiber in a different fashion than in fibrograph, and mean length can also be measured by measuring the fiber length, individual fiber length, and then take the average. Next is the upper quartile length, that we will discuss. Then effective length, modal length. Modal length is basically where it is a particular length where majority of fibers are in that particular range. Span length, the concept I will discuss. Upper half mean length, this we will discuss. Okay. So in addition to the fiber length characteristics, length parameter, like what is the mean length, the natural fiber, in case of natural fiber, fibers are not of same length. In a particular, say, cotton tuft, if we see, this is cotton tuft, if we see the fibers are mixture of longer fiber, shorter fibers are there. This type of mixed lengths are there. So we must know the variability of the fiber length. So this variability can be expressed by dispersion percent. Dispersion percent we get from comb sorter diagram. Then uniformity index we will discuss. This we get from fibrogram. Uniformity ratio, short fiber content, floating fiber index. These are the parameters through which we express the variability in the fiber length, and fiber length variation estimation is extremely important, because the higher the variability, higher will be the floating fibers, and that results the non-uniformity in the yarn, and higher content of short fiber results the breakage, and the hairiness also increases. So there are various characteristics here. If we see the equal fiber length for say cut polyester, cut man-made fiber, the spinning of these fibers are easy, because the roller setting is easier. We can set roller setting depending on the cut length. But when the variability is very high, the roller setting is a problem, because if we set based on the longer fiber, then there will be many floating fibers which will create the unevenness. Now we will discuss this term one by one. The staple length, as I have mentioned, it's defined by the United States Department of Agriculture, USDA, as the normal length of typical portion of staple fibers. Staple fibers means short fibers. Okay. What does it mean? If we do repeated doubling and drawing, so we will get this type of fringe. Now let us see the fringe, how is it looking like. So the fringes will be like this. The short fibers will be at the center, and the concentration of the fibers will be higher at the center position, and gradually it will reduce. Now if we see the density of fiber from the edge side, gradually it is increasing. If we go this side, gradually it will increase, and there will be certain point where we will find that sudden increase in the density, that is concentration of fiber or number of fibers. Similarly, if you go from the left side, we will see that we can draw a imaginary line where sudden increase in the number of fibers are there, and the distance between these two is called staple length. Okay. So we can see that it doesn't mean that it's a longer fiber. So longest fiber, the long fibers are not the basic idea here. It's a basically the typical portion. So where this is called the typical portion of fiber. We are not concentrated on the measuring the mean length or longer fiber length, but typical portion is there where suddenly concentration has increased. So we can see here, if we go from the edges, so it will be there. So this is the concept of staple length. But the problem is that it's a subjective in nature. For same cotton sample, the different person will have different interpretation. So based on the staple length, cotton can be classified as per USDA. Short fiber less than 20.6 millimeter like this, and 34.9 and more, it's a extra long fiber. So this is broad classification. Next parameter is mean length. Mean length is the average length of all fibers in the specimen based on weight length data. There are two types of mean length. One is weight length data and another is number length. So mean length based on weight length, that this I will also discuss later. So in shorter diagram, the say for cotton fiber, this lengths are, fibers are distributed as per the length, okay, starting from longer length to shorter length. And what we are doing, we are at different classes. This is a longer length, this length class is say L1, and then we take the mass of the fiber W1. This length class will be say L2 and we take the weight W2. In this way we keep on doing W3, the length class is L3, and we can divide into different length classes. Class may be say within 3 millimeter length. Within 3 millimeter length we take these fibers and take the mass. In this way we take the entire fibers, all the fibers we take, and based on the weight we can measure the mean length. And this is important for actual running purpose. In spinning what we do, we don't measure the number of fiber. It's very difficult to measure the number of fiber, but we can take the weight of fiber, okay. So that is for analysis of waste percent or comber noil percent. This mean length based on weight is important. Next parameter is number length, where number length is very straightforward based on the number. Suppose L1, so 3 fibers are there, 1, 2 and 3, L1, L2 and L3. So simply we can add and divide by 3. This is number. Now L1 length, suppose L1 length zone. Earlier case we have measured the weight. Now here for L1 length class, suppose the number of fibers are N1. For L2 length class, number of fibers are N2, N3. So here the relationship will be L1, N1. So total length of L1 class, L2, N2 and L3, N3 divided by N1 plus N2 plus N3. This process actually it's tedious, it takes longer time, whereas the mass based is quicker. So we simply take the mass of the fiber. So number of fibers counting is very difficult. Upper quartile length. So this upper quartile length is defined as the fiber length which is exceeded by 25% of fibers by weight in the test specimen. This is the definition. Now the meaning is here, again we are forming the fiber length distribution. This is a number of fibers and here it's a length. Now again we are distributing fiber lengths are distributed. Now suppose the total weight of this fiber is W, whatever we have taken, and now we go on taking fiber from the longer side and taking mass. So this we are taking, this bunch we are taking, gradually we are removing these bunches and we have removed these bunches. Okay, after removing whatever fibers we have removed, these are the fibers we have removed. Whenever this mass of this fiber is W by 4, that means this is the fiber length beyond which the total mass of W by 4, and this length, it's the upper quartile length by weight. That means the fiber length which is exceeded by 25% of fiber by weight. And these are some guidelines. Upper quartile length is always more than the mean length. Okay, mean length, because mean length takes care of the short fibers also. So these are the typical classification. 7.9 less than that we can consider is at short fiber. 35.3 is the extra long fiber. So these are some guidelines. short fiber content. This is the quantity, that's weight of fibers having less than ½ inch length. So this with the red zone, where the if you take the total mass, suppose this is the total mass of the fibers is W, and this is short fiber is small w, and it will be 100 is the short fiber content. Percentage by number. So by weight and also by number we can measure. Number of fibers, suppose there are 10,000 fibers are there in this distribution, and we can calculate the number of fiber, we can measure the number of fiber x. So we can number of fibers are shorter than ½ inch, and this short fiber content is important for roller setting, and it will indicate the floating fiber. So floating fibers are the fibers which are not gripped between the drafting roller. So this is the front drafting roller, this is a back drafting roller, and during drafting this red color fibers are floating fibers which are not gripped, they move by the cohesion, the frictional contact with the adjacent fibers. And we can express the floating fiber index now. After discussing the fiber length parameters, now let us try to discuss the methods of measurement. First is hand stapling method, that I have already explained, and it has to be carried out by a trained person in this fashion. Now let us see that first selecting a sample of cotton and preparing by hand doubling and drawing. So you select the cotton and then prepare by hand doubling and drawing to give fairly straight fiber strand. Okay, the width of this fringe is typically 1 inch. Typically 1 inch width we are preparing. Then we place this fringe on a flat black background so that we can see the presence of fibers clearly, and staple length is measured, that as I have already explained. Like we cannot take the extreme tips, that means suddenly the change in the density of the number of fibers. So the classer chooses the length where there are reasonably well defined edges, as we have discussed. Suddenly there is a change in the density, that is well defined edges. It doesn't take the extreme end into consideration. So subjective nature, so it result varies. Now, due to the subjectivity of the hand stapling method, mainly subjectivity comes in defining the edge point. So here this is a so this the lines between these two lines, as I have discussed. So this identify these lines are important, and where if we make some mistake here, that will affect the staple length. So automated version of the hand stapling method is there, which is Surly photoelectric stapler. It's a faster measurement technique, and which is there is no subjectivity. Objectively we can measure, so variability is least. Now try to see the animation. I will show you the animation. The sample first is kept on the a black velvet pad. The thickness of the fringe should not be too much. So here one important thing is that so that light can pass through the edge at least. So if we make the fringe very thick fringe, it will not be able to give the correct result. So suppose I am making a thick large number of fibers I am taking, then we will not get the actual result. So number of fibers we have to select, that the traces of black velvet can be seen through the central part where density is highest. That means we are taking the number of fibers, at the back side there will be black velvet that can be seen from even from the central part, because it works on light reflection method. And the photoelectric method detects the densities distance between the density gradient, like it detects the at the edge. So density gradient from the and the right side and left side, that at the edge it will detect. Now we can see the animation here. So light source is coming, and where light is splitted into two parts, double slit splitter, and then it's getting reflected to a mirror, and it's falling on a particular point. So there are 2 points will be there. Now fiber fringe which is prepared separately is placed on a conveyor belt, and this is moving, and the light from the 2 points, the 2 point distance may be very small distance, maybe 1 millimeter distance, and that will reflect the light to the 2 photoelectric cell, and that will this photoelectric cells are connected with the galvanometer, and depending on the densities, the extreme end where sudden change in densities are there, so this will be able to detect the to edge point where sudden change in densities are there, and that will be calculated based on the speed of the conveyor belt and time required to have the opposite signal. So these are explained here. 2 photoelectric cells are connected in opposite to each other. Depending on the light intensity, the opposite cells pass a current which is proportional to the difference in intensity. The variation in current is shown in by the sensitive indicator. The fringe is advanced inside the instrument to maximum density gradient point will be there, and this distance is staple length. So this is the automated version of the manual hand stapling technique. And effective length, typically it's 1.1 times of the staple length. Now the next technique is the comb sorter technique. Now in comb sorter, the fibers are arranged in the descending order of the length. So longest fiber will be placed at the left side, and gradually all the fibers are arranged in this fashion. This is for typical comb sorter diagram for cotton. Now let us see here. Now fibers are arranging. We are arranging the fibers by the comb sorter process, and then the analysis we can do that. You can see the longest fiber, the midpoint of the longest fiber, that is OQ, which is half of OA. From there we draw one horizontal line which is intersecting at the point P dash on the comb sorter diagram. Then we are drawing a vertical line, and in this way we will continue, and this process is explained separately. You can just go through, but here basic idea is that we are able to calculate the or measure the effective length of the fiber, and which is done by the, it's a second approximation. So first approximation is K dash, the length, it's a upper quartile length, and it's a second approximation of the upper quartile length. First approximation is done by this process, which is that you just take the midpoint of OA, then it is going to horizontal line is touching at P dash point, then take the this line is then P dash is a vertical line on the axis x axis, then P we are dividing, OP we are dividing into 4 parts, equal parts. The upper quartile OK, OK is the 1/4 of OP, then we are drawing one vertical line which is actually intersecting the at K dash point. Again this is the first approximation, and then second approximation, first approximation of the upper quartile length. Now second approximation, we take the midpoint of K dash, which is S, again doing the same thing, and OR, that then OL is the point which is 1/4 of OR, and if we take the vertical line, so L dash is the second approximation of the upper quartile length. So this is defined as the effective length. Now the lower quartile length of second approximation is M dash, where OM is 3/4 of OR. So OM is 3/4 of OR, that means M dash is the lower quartile of in the second approximation. Now the difference between L dash and upper quartile and lower quartile length, which is known as the interquartile range. So L dash minus M dash, if we see, it's L dash N, that is the range, interquartile range, and that divided by the effect that divided by the L dash, which is effective length, that is known as the dispersion percent. Now if we see here, this is the suppose effective length, and here this point is the lower quartile length or upper quartile length, and if we, so interquartile range means upper quartile length minus lower quartile length. This difference, this distance is actually showing the dispersion, how the length is varying. Now say 2 fibers are there, this is one fiber, another fiber is like this, where this is the upper quartile length and here it will be a lower quartile length. And if you see, the variability is very low, and dispersion percent is nothing but the upper quartile length or effective length. So dispersion, by the term dispersion, we can actually indicate, we can measure how the length is varying. So any flatter mid zone which will indicate the lower dispersion percent. So comb sorter we have discussed. So these are the parameters which we have got. So short fiber percent what is the short fiber percent? So these are the number of short fiber which is less than the lower quartile length based on the total number of fiber. So Gx by Ox, short fiber percent by number. So here assumption is that we are arranging all the fibers into equal distance, so that number of fibers density throughout the plot is equal. And interquartile range we have already discussed, dispersion percent. So dispersion for a flatter mid zone we have already discussed. So flatter mid zone will have lower dispersion, so that means the fiber will perform better during the process. So higher dispersion percent means poor quality. Effective length we have already discussed, we are not going to discuss here. So this is the, it's a second approximation. So upper quartile length of the fibers distribution obtained by ignoring the short fibers. So this is the upper quartile. And dispersion percent is that interquartile range divided by effective length. So by knowing, this is actually this dispersion percent and effective length. If we know, if we have the data, two data, one is effective length and dispersion percent, we can act from these two data we can make out the nature of the cotton fiber as far as length is concerned. So higher dispersion will have, this is the one, and so maybe say three different curves are there. Okay, the same distribution, suppose here this will have lower dispersion purpose and this will be higher dispersion percent. So this red type of fiber, this fiber, say this type of fiber will create problem during the process. Now let us try to do some numerical. So in a cotton fiber length testing by comb shotter, the lower quartile length is 19 mm and the dispersion percent is 20%. The effective length is to be calculated. Okay. Now this is upper quartile length, here it will be lower quartile length. Okay, and upper quartile length means effective length and lower quartile length which is 19 millimeter. So dispersion percent 20, effective length by minus 90, 19 divided by effective length. So from there, this equation we can calculate the effective length. We can see here the dispersion percent. So effective length minus 19, and by solving this equation we can get the effective length value of 23.75. Okay. Now in this numerical, if we see, if we increase the dispersion percent, keeping the lower quartile length same, and if we want to increase it's a 30%, 30% dispersion. That means, so the difference will be, so what will be the value? Effective length minus 19 by effective length (30). Okay, so 0.70 effective length equal to 19. Effective length will be 27.1 mm. So now our effective length is increased to 27.1. This is the 27.1 second, and earlier was that. This is yarn fiber 2 and this was fiber 1, initial fiber. Now which one we have to select? This fiber, the fiber 2, although it is giving the higher effective length, but the roller setting is done based on the effective length, and when we are getting this the fiber 2 will be expensive, more expensive, and when we set the roller, we cannot set the roller, if we have to set the roller based on the effective length, the roller setting in the drafting. And so when we set the roller based on this effective length, the floating fibers will be more in fiber 2 due to the dispersion percent. So ultimately product quality will be deteriorating, although we are giving higher price. So dispersion percent is extremely important to be considered. Now let us do another numerical. Similar numerical is that in a cotton fiber testing by comb sorter, the lower quartile length is 25 and dispersion percent is 25, effective length. Similar way we can calculate. So you can see here, as compared to earlier numerical, so as we have explained, that when we are having higher upper quartile length, earlier case upper quartile length was 19, so lower quartile length was 19, here we are having better fiber, and let us see the earlier data, 25 and 20% was the dispersion percent. Here we are using higher dispersion, fiber dispersion percent is higher, still we are getting effective length more because of the lower quartile length. Now try to see the similar problem here. Comb shorter, dispersion percent is given and effective length is given. So this is the effective length, here is the lower quartile length L, Q, L. So dispersion percent equal to interquartile length, that is effective length minus lower quartile length by effective length 100, which is dispersion percent is 23% and effective length is 35. Here we can see that the lower quartile length in the same way it is 26.95 millimeter. Next parameter here is that modal length. The modal length is basically the term came from the term mode. Mode in statistics means the particular element with higher frequency. The length with high frequency. In the sample obtained from the fiber length frequency diagram. Now, if we see here fiber length frequency diagram, if we draw, this is the diagram. So here if we see, if we take this midpoint here and we will plot one curve, then again you take midpoint, this is one length group L1, this is another length group L2. So you take the midpoint, so you will see the distribution here is very high. So this will be the modal length. So the fiber, you can see here, if we try to distribute the fiber, we can form the histogram here. The wider histogram, that means the number of fibers are more, maximum in this length group. What is this length group? Here is the length group. So this is the length which is known as the modal length. So we will stop here for today. So we will continue with the fiber length analysis in the next session. Thank you.